it away. Okay. Hello, everyone. Today, I'm happy to present our work on testing and exploring bugs in zero-knowledge compilers. Think about the last time when you have to prove something, like showing the bank that you are eligible to open a bank account, or a company to demonstrate its regulation compliance. But in each case, you probably revealed more information than necessary. For example, you reveal your entire salary slips just to show that you earn enough. What if we could prove something without revealing sensitive data, like a company showing its regulatory compliance while protecting its confidential data, or a country demonstrating its carbon neutrality while protecting its industrial data information? That is what zero-knowledge proofs come in. They let us prove something while protecting privacy. Let's stick with our bank example to show how we can open a bank account. The prover, who is the bank, has a constraint that any successful applicant for the bank account must earn over than $2,000 per month. The applicant, who is the prover, wants to keep his exact salary secret. In ZK, the constraints are then mapped to the mathematical puzzles. These puzzles are special. They can be only solved if your secret information matches the constraints. The prover then tries to solve this mathematical puzzle using his secret information, which is his salary, and create a proof based on that. The verifier, which is the bank, takes this proof and checks whether it actually solves the math puzzle. If it does, the bank has confidence that this applicant meets the income requirements. On the other hand, if the income is less than the requirements, then most likely the prover won't be able to solve this mathematical puzzle and the verification will fail. Here's the magic. Through this verification process, the verifier never sees the actual salary information. That is what zero knowledge is about. In typical applications, the constraints are expressed using specialized ZK programs, which are written in domain-specific languages. We show an example for such language examples, and in this example, the bank asserts that the net income should be more than $2,000 based on the tax allowance and the gross income of the applicant. The DSL of ZK supports visibility modifiers. For example, the tax allowance is assumed to be public knowledge from the taxation systems, and it is visible to both the verifier and the prover. On the other hand, the gross income is private and is only visible to the prover. You can specify constraints by using the assert statements to assert that the net income is greater than $2,000. Well, the ZK program will then be mapped to the math puzzle. However, for efficiency considerations, the math puzzles are typically encoded in a specialized arithmetic circuit called ZK circuits. The conversion between the program and the circuits is handled by a special software called ZK compilers, which are responsible for translating the high-level source program into the low-level circuits. The ZK compilation is a complex process. Unlike traditional C compilers, where the translation targets are machine code, the translation targets for ZK are ZK circuits. And so the translation process requires specialized optimizations that are unique to the zero-knowledge proof systems. The correctness of ZK compilers is essential. A properly compiled system should reject those applicants with only $1,000 income. But a compiler bug can break this security guarantee. It can lead the unqualified applicants to be classified as qualified, and the bank may get some financial losses by opening bank accounts for those unqualified applicants. In fact, we have seen several major blockchain systems which are using ZK compilers in their system, and they suffer from those ZK compiler bugs. So this brings us to the key question: how can we automatically test ZK compilers to ensure their correctness? However, this problem is not easy. We face the ground truth problem. That is, how can we decide that the compiler does its job correctly? So what do we mean by correctness? It means that the high-level program should have the same semantics with the compiled circuits. Any semantic discrepancy means a compiler bug. But proving the semantic equivalence between the high-level program and the low-level circuits is a hard problem. It's generally difficult to develop a solution for arbitrary ZK programs to prove the equivalence with their corresponding compiled circuits. So instead of solving this hard problem of proving equivalence, we try to compare the compiler with itself. So how do we do that? We could design a set of relations, and we mutate the programs in such a way that the original and the mutated programs satisfy our predefined relations. We then compile those two programs with the ZK compiler on the test into the ZK circuits. If the program has the same semantics as the circuits, then those relations should also hold for the circuits, because actually the program and the circuits are semantically equivalent. If they do not hold for the circuits, then we know that the semantics of the circuits is not equivalent to its original programs, and we know that the compiler has a bug. How can we implement those predefined those relations? Well, the first relation we implement is based on the satisfiability invariance. That is, we can insert some always satisfying relations into the high-level source program, like asserting that the value of a number should not exceed the maximum of their data types. Such constraints should always be satisfied, no matter what input you get. We then compile those two programs into the circuits, and ideally, those constraints should also be always satisfied in the circuits. But if we can find an input that violates those constraints in the circuits, we know that the constraints are not properly compiled into the circuits, and the compiler is not doing a good job in compiling those constraints and has a bug. To implement this, we can take this basic example to show how do we do that. Initially, there are no constraints in the program. We can add a constraint by saying that x should be less or equal to the maximum of its data type, which is integer. We can also add another tautology constraint saying that x is equal to x times 1. We can even do some runtime profiling and assert that the variable should be equal to its runtime value, like asserting that x is 76 at line 12. We can also create other variants of the constraints by using double negation. And we can combine the single constraints using conjunction. So by iteratively applying our mutations, we can obtain very complex ZK programs that can thoroughly stress test the ZK compiler implementations. The other mutation we propose is based on the information visibility that are inherent to the ZK problem. So in ZK, the plaintext, the public inputs can be stored in plaintext, while the secret inputs must be encrypted to avoid the privacy leakage. So ZK compiler has a crucial job in separating those two information visibility and applying the corresponding organizations according to their visibility. We can exchange the visibility of the inputs, and no matter how we exchange the visibility, we must know that the outputs of the program is not affected. If we see that the outputs of the circuits from the corresponding mutated program is changed, then we know that the compiler mishandles the semantics of the program, and there's a compiler bug. To implement this, we can substitute constants in the program, which are public information with public inputs, or we can substitute them with private inputs. To evaluate our implementation, we select 4 mainstream ZK compilers. Those compilers are used in high-valued blockchain systems that are securing billions of dollars in total. Overall, we discovered 21 bugs in those 4 compilers, with the majority of them being fixed. This is a critical bug we found in the ZK compiler. Ideally, a user cannot in a bank scenario, the programmer may specify that the withdrawal amount cannot exceed their savings. However, we found that the compiler mishandles these constraints, and after the compilation, will input the maximum of the integer type to the circuits. These constraints will be bypassed regardless of the actual savings in your account. This bug arises from the mishandling of the public finite field data types during the compilation process. Another bug is related to the division by zero. Division by zero is well defined in ZK, which should return an error message. However, the compiler suddenly sets the average salary to be 0 at line 11. So the constraint at line 13 is always passed, regardless of the result of the average division by n. So the attacker can compose a backdoor by using this compiler bug, and then by inputting a magic password, this bug will be triggered, and the attacker will be classified as a low-incomer to receive unwanted benefits. So in summary, we're the first piece of work to conduct a study to uncover bugs in ZK compilers, and we propose 2 mutations that are specific to the zero-knowledge proof systems, which are inserting always satisfying constraints, and another one is mutating the information visibility of the inputs. In total, we discovered 21 bugs on 4 mainstream ZK compilers. Thanks for listening, and I'm happy to take any question.
The talk, we have time for a couple of questions. If not, I have a couple of questions. Thanks for a very clear and nice talk. This is a neat idea. I'm wondering how, when you were looking for bugs, how did you choose what invariants to kind of do? Because it looks like there's some human intuition needed to guess what invariants and what relations to test out.
Oh yeah, by far we use human-defined rules like some tautologies, like x equals to x times 1. Yeah, so you can basically define any kind of tautologies that you can that are always true. But in total, we define like over 10 or something like rules for that. But you can define any tautology that you want. But we envision that in the future, we can also develop automated like tautology generation schemes for that. Yeah.
Cool. And go ahead.
Just a small comment. You may consider using some work from obfuscation. There are a lot of techniques of adding tautologies, basically. So you can just use these many techniques to add tautologies, right?
Yes, we also are aware of some works for that. Yeah, especially in the PL community, and they have great jobs in those fields. Yeah.
I had one more question. Are these compilers compiling to arithmetic circuits or to like rank 1 constraint systems? I'm curious. I'm wondering if these techniques can also be used for compilers for MPC, or if it's kind of specific to zero knowledge.
Well, I think this technique is like because MPC doesn't have constraints, they don't prove properties. So probably our methods may not be applicable to MPC. Yeah.
Got it. So it's not compiling to like an arithmetic circuit. It's compiling to a constraint set of constraints.
Yeah, exactly.
Got it. Thank you so much.
Yeah,
Let's thank our speaker one more time.